This line is about scheduling yard cranes, meaning deciding which crane will do which container move, in what order, and when. In the yard, every lift is part of a chain. A single late move can delay a truck, disrupt a rail departure, or force a vessel loading plan to wait. When you hear orchestrating container moves in the yard, think of a live operating system. The goal is not only to finish all moves, but to finish the right moves at the right time, while keeping cranes safe, non-interfering, and productive. Yard cranes are the bridge between seaside work and landside flow. They connect vessel discharge and loading to trucks, rail, and storage blocks, so their schedule becomes a direct lever on vessel turnaround time and terminal throughput. Small inefficiencies compound fast. If each decision adds a little extra empty travel or a little extra waiting, that error gets repeated across thousands of daily moves, turning into measurable congestion, missed appointments, and overtime pressure. Imagine a morning shift at Maasvlakte 2 in the port of Rotterdam. In this scenario, 26 rail-mounted gantry cranes coordinate the movement of more than 2,400 containers across 68 storage blocks. The key physical rule is the non-crossing constraint. Adjacent cranes cannot pass each other. That turns scheduling into a routing and sequencing problem with interference, because a plan that looks good in isolation can become impossible when two cranes would need to occupy the same corridor. This slide contrasts rubber-tired gantry cranes and rail-mounted gantry cranes. Rubber-tired gantry cranes are mobile, so they can serve multiple blocks, which gives flexibility but increases coordination complexity. Rail-mounted gantry cranes are fixed to a block and behave like automated stacking cranes. You trade mobility for predictability, and the schedule must respect fixed corridors, safety separation, and the fact that cranes cannot simply go around each other. Scheduling is not only about distance, it is also about time. Requests arrive with deadlines driven by vessel departures and truck appointments, and a container needed in 2 hours is more urgent than one needed next week. Storage decisions today also change retrieval effort tomorrow. If you stage or place containers poorly, you create future work such as extra repositioning and longer travel. So the schedule must anticipate downstream consequences. This deck is organized as a tiered toolkit. Tier 1 provides a vehicle routing style formulation with time windows and precedents. Tier 2 provides the cheapest insertion heuristic. And Tier 3 uses the Grasshopper optimization algorithm. Tier 4 introduces neural architecture search for prediction. Tier 5 embeds scheduling into a system of systems digital twin. Tier 6 uses a multi-agent ecosystem. Tier 7 adds a human and artificial intelligence partnership. And Tier 9 frames the problem as quantum annealing via quadratic unconstrained binary optimization. Tier 1 frames yard crane scheduling as a vehicle routing style problem. Jobs are container operations, and each crane runs a route through jobs over time. The model includes time windows, sequencing, travel time between job locations, and safety separation. The point is to make feasibility explicit so any computed schedule can actually be executed on the ground. The sets define what objects exist in the model. Here that means the set of jobs, the set of cranes, and the set of yard locations or bays. Operationally, sets prevent ambiguity. If a job or crane is not in the set, it cannot be assigned, sequenced, or measured. So the sets are the boundary of what the plan covers. Parameters are the facts you do not control but must respect. In this formulation, they include travel times between job locations, processing times for each job, release times, due dates, priority weights, and each crane's starting position. Operationally, these parameters are where the terminal operating system feeds the optimizer. Job timing windows, estimated crane cycle times, and the physical layout that determines travel and interference. Decision variables represent the choices the schedule makes. At a high level, the model decides which crane performs each job and in what order, so that each crane's route is well defined. It also tracks the start time and completion time of each job. Those timing variables are essential because the real performance measure is not just which jobs are done, but whether they are done before their deadlines. The objective combines two costs. One part penalizes lateness, weighted by job priority. Another part penalizes travel time between jobs. Operationally, this objective encodes a realistic trade-off. You want urgent moves served on time, but you also want to avoid excessive empty travel because travel consumes capacity without completing a job. The first term is priority-weighted tardiness. This pushes the schedule to protect high-priority jobs, such as moves tied to an imminent vessel departure or an appointment window. The second term is travel cost. This discourages schedules that bounce cranes around the yard. The combined effect is a schedule that is both punctual and efficient, instead of optimizing one dimension while ignoring the other. The assignment constraint enforces that every job is handled. Each job must be assigned to exactly one crane. Operationally, this prevents dropping work or duplicating work. Dropped jobs become missed pickups, and duplicated jobs become double handling, both of which are failure modes that a mathematical model must explicitly block. If assignment is not enforced, the model can improve the objective by pretending some jobs never happen, or by assigning multiple cranes to the same job. In real operations, that would show up as missed truck service, an incomplete vessel loading sequence, or unnecessary handling that wastes time and increases risk. The start constraint defines that each crane route begins properly. Each crane must have a defined first job after its starting position. Operationally, this anchors the schedule to reality. Cranes do not appear in the middle of the yard. They start from known corridors or initial positions. Flow conservation enforces continuity of each crane route. If a crane arrives at a job, it must also leave that job to go to a next job, except at the end. Operationally, this eliminates disconnected schedules that cannot be executed. A plan must be a continuous sequence of moves for each crane, not a set of isolated assignments. The end constraint closes each crane route. It ensures each crane has a defined termination of its route rather than an unfinished path. Operationally, this matters for shift planning and for feasibility. You need to know when a crane is free, where it ends, and whether it can be repositioned or released for maintenance. Start and end constraints create a valid route for each crane. Flow conservation ensures the route is continuous from one job to the next. Together, they prevent a common model failure, a schedule that assigns jobs but does not define an executable sequence, leaving gaps that would require manual intervention or cause idle time. Timing constraints connect the route to the clock. Jobs cannot start before their release time, and completion time is start time plus processing time. Sequencing constraints ensure the next job cannot start until the previous job is completed, and the crane has traveled to the next job location. Release time prevents starting jobs before prerequisites are available, such as a container not yet discharged or a truck not yet arrived. Completion time ties the schedule to processing time, and the sequencing constraint prevents overlap. Together, they block impossible plans where one crane would be in two places at once or would teleport without travel time. This slide introduces the safety distance constraint. Adjacent cranes must maintain a minimum separation while operating. Operationally, this is what converts an efficient schedule into a safe schedule. Without safety separation, the plan may look good numerically, but would create collision risk or force emergency stoppages. Safety distance is a hard operational requirement. Cranes in adjacent blocks or corridors cannot operate too close together. This constraint also supports non-crossing behavior in practice. If cranes cannot violate separation, then passing each other becomes infeasible, so the schedule must respect corridor ordering. This visualization shows a vehicle routing style view of yard crane scheduling. Think of each crane as a vehicle and each container operation as a job node. The operational value of the picture is clarity. It helps you see how route design, travel, and timing interact, and why the scheduling problem is not just assignment, but also sequencing and movement. This small example makes the timing logic concrete. Job 1 has release time 0 and processing time 3 minutes. Job 2 has release time 2 and processing time 2 minutes. Job 3 has release time 1 and processing time 4 minutes. Travel between adjacent positions is 1 minute, and the optimal schedule completes all work in 8 minutes with 0 delays. The key lesson is that respecting release times and travel time is what turns a list of jobs into a feasible schedule. Tier 2 uses the cheapest insertion heuristic to build routes incrementally. At each step, you insert an unscheduled job into a partial route at the position that adds the least additional cost. Here, cost includes added travel, added processing implications, and weighted delay penalties. Operationally, this makes it a practical real-time method. It makes good local decisions quickly. This slide is about complexity. The key idea is that insertion heuristics can become expensive as job count grows, because each new job may be tested in many possible insertion positions. Operationally, complexity determines whether you can use the method in a live terminal. If the heuristic is fast enough, it can replan frequently as new requests arrive. This flow diagram shows cheapest insertion as a process. Start with empty routes, pick a job, evaluate where to insert it, choose the best insertion, and repeat. Operationally, the diagram highlights the main value. The heuristic is structured enough to be implementable and explainable, yet flexible enough to adapt as the yard state changes. This slide begins the implementation details. Focus on how the heuristic computes the incremental cost of inserting a job into a route. Operationally, the cost calculation must reflect what the terminal cares about: urgency, travel, and delay, not just distance. This slide continues the implementation details, including how routes are updated after an insertion is chosen. Operationally, the update step is where feasibility is protected. If a new insertion causes timing conflicts or unsafe interference, the heuristic must reject it or apply a repair rule. This example reports metrics for 5 jobs and 2 cranes. The final solution has make span 14 minutes, average delay 1.2 minutes, and crane utilization 78%. It also claims performance within 15% of optimal, computed in milliseconds. Operationally, that is exactly why heuristics are valuable. Fast decisions with acceptable quality. Tier 3 uses the Grasshopper optimization algorithm, a swarm meta-heuristic. Each Grasshopper represents a full multi-crane schedule, not just one insertion step. The method shifts from exploration to exploitation using a decreasing coefficient. Operationally, that means it searches broadly early on, then focuses on refining good schedules. This slide contains the update equation concept for the Grasshopper method. The key idea is that candidate solutions move in the search space under a mix of social interaction and attraction toward the best-known solution. Operationally, treat this as the engine that improves schedules over iterations. It is how the algorithm balances global search with local improvement. This slide visualizes exploration and convergence. Early iterations explore diverse schedules. Later iterations concentrate around high-quality regions. Operationally, you are looking for 2 signals: steady improvement in the best schedule found and controlled reduction in diversity so you do not get stuck too early. This is the first pseudocode segment for the Grasshopper optimization algorithm. Focus on initialization and how schedules are encoded as candidate solutions. Operationally, initialization quality affects speed. A better starting population means fewer iterations are needed to reach usable schedules. This segment typically covers fitness evaluation. Fitness should reflect what the terminal values, such as make span, delays, and travel. Operationally, if fitness is misspecified, the algorithm will optimize the wrong outcome and produce schedules that look good on paper, but disappoint in execution. This segment focuses on the update step and coefficient decay. The coefficient controls how aggressively solutions explore versus converge. Operationally, you tune this to your planning horizon. If you have seconds to compute, you can explore more. If you need immediate decisions, you converge faster. This segment completes the main loop and output handling. Operationally, you also need stopping criteria. You stop when improvement stalls, when a time limit is reached, or when a required quality threshold is met. This instance uses 15 jobs and 4 cranes. The initial average fitness is 156.7 minutes, and the best initial fitness is 142.3 minutes, with diversity 87%. By iteration 150, best fitness reaches 119.4 minutes. The reported improvement is 16.6%, with computation time 4.2 seconds, showing that meta-heuristics can trade compute time for better schedules. This slide summarizes reported gains: 31% improvement versus random assignment, and 12% improvement versus a greedy heuristic. Operationally, that trade-off is typical. You pay seconds-level compute time to reduce delay, travel, and idle time beyond what a fast heuristic can achieve. Tier 4 predicts scheduling decisions using models discovered automatically. A controller network samples architectures and is rewarded for validation performance. Operationally, this replaces hand-designed models with architectures tuned to terminal data. The promise is fast inference once trained, so decisions can be made in real time. The state includes crane positions, the pending job queue, block occupancy, and stack heights. It also includes traffic patterns, weather conditions, and equipment health indicators. Actions include job-to-crane assignments, sequencing, pre-positioning, and dynamic priority adjustments. Operationally, this defines exactly what information the model sees and what decisions it is allowed to make. This visualization shows an enhanced routing view for yard cranes. It helps connect the learning model's decisions back to physical corridors and travel. Operationally, this matters because a learned policy must still respect safety and interference. The picture helps you sanity check whether suggested moves are physically plausible. This is the first implementation segment for neural architecture search. Operationally, focus on how candidate models are generated and evaluated. The system must compare architectures fairly, otherwise it will converge to models that look good due to training artifacts. This segment continues implementation details. Operationally, pay attention to how training and validation are separated. A model that performs well only on training data is not useful for live scheduling. This segment continues implementation details. Operationally, the search process must explore enough variety. If the search space is too narrow, the best architecture may never be considered. This segment continues implementation details. Operationally, this is where compute control matters. You need to limit search costs because training many architectures can be expensive. This segment completes the implementation sequence. Operationally, the output is not just a model, but a repeatable pipeline. Define search space, run evaluation, select the best architecture, and then retrain it for deployment. The discovered architecture includes a one-dimensional convolution with 64 channels and batch normalization, followed by a 3-layer bidirectional long short-term memory network with 128 units and multi-head attention with 8 heads. It uses multitask outputs for assignment, sequencing, and prioritization. Operationally, this is a practical design. One shared representation supports multiple decisions that must stay consistent. Training data includes 50,000 historical decisions from the Port of Hamburg. Reported job assignment accuracy is 94.2%, sequence prediction accuracy 91.7%, and priority adjustment accuracy 89.3%. Inference latency is 12 milliseconds per decision, and model size is 2.1 million parameters. Operationally, that latency supports real-time use. Reported impact includes 18% reduction in average job delays, 22% improvement in crane utilization, and 15% decrease in vessel turnaround times. The reported gain over manually designed networks is 7 to 12%, while staying under 20 milliseconds. Operationally, that is the difference between a research model and a deployable decision tool.